Hey there, and welcome. So if you're getting serious about physics, you already know that as the ideas get bigger, the math can get, well, really messy. Today we're going to demystify one of the most powerful tools physicists have to clean up that mess, index notation. Seriously, think of it as a secret weapon that can turn pages of painful algebra into these short, elegant, and really insightful lines. Let's jump in.
I'm sure you've all seen this one before. It's the famous BACAB rule for the vector triple product. It's just one of those fundamental truths in vector algebra, right? It pops up all over the place, from mechanics to E&M. We all know it's true. It's hammered into us from the textbooks.
But what if I asked you to actually prove it, like right now? Your first thought might be to just brute force it. Write out vector A as AX, AY, AZ, and B as BX, BY, BZ. You get the idea. You'd calculate B cross C, then cross A with whatever that result is, and it would just be an absolute nightmare of algebra. We're talking pages of work, with a million little places to make a tiny mistake that just ruins the whole thing. There's got to be a better way.
And of course there is. So here's our game plan. We're going to see exactly why we need a new approach. Then we'll introduce the core shorthand that makes it all possible. We'll define the special tools that give it its power, and then we'll use all that to master vector operations. We'll even cover the common mistakes people make before we do a final recap. And trust me, by the end of this, you'll be able to prove that BACAB rule in just a few lines. It's pretty cool.
Okay, so first up, let's really dig into the problem. Standard vector notation with the little arrows on top, it's great. It's fantastic for visualizing things in 2 or 3 dimensions. But the moment you have to do a serious proof, you start to see its limits, and fast.
And this right here is the heart of it. When you're forced to write out every single component, you're not really working with the vector as a single idea anymore, are you? You're just juggling 9 or more separate variables. The algebra gets so long and clunky, and honestly, it hides the beautiful geometric ideas underneath. We need a better system, one that keeps the components nice and compact and makes the rules for manipulating them totally systematic.
And that brings us to the absolute core idea of index notation. It's all about creating this incredibly powerful, really elegant shorthand for vectors and their components. And it all kicks off with a really simple idea.
So instead of always writing Vx, Vy, and Vz separately, we're just going to talk about the ith component of a vector v, which we write as v sub I. This little index I is basically just a placeholder. If you want the x component, you say I is 1. For the y component, I is 2, and for the z component, I is 3. It seems like a tiny change, but this is the first step. The real magic, though, is what comes next. This is it. This is the single most important rule of the whole game. It's called the Einstein Summation Convention, and it's brilliant. What it says is that anytime you see an index that's repeated, so it shows up exactly twice in one term, you don't have to write a big old sigma for summation. It's just implied. The summation is automatic. It's a convention that just cleans up our equations like you wouldn't believe.
Okay, let's see this in action, because this is where it clicks. Look at this expression. A sub I times B sub I. See that? The index I appears twice, once on the A and once on the B. That means the summation convention kicks in. So this tiny little shorthand, A sub I, B sub I, what it actually means is set I to 1, then set I to 2, then set I to 3, and add all those pieces up. So we get A1B1 plus A2B2 plus A3B3. Well, what is that? That's just the definition of the dot product, A dot B. So that compact little A sub I, B sub I is just the index notation for the scalar product. So cool.
Okay, so this slide right here breaks down the 2 different jobs an index can have. This is super important. If an index shows up only once in each term, we call it a free index. So in an equation like AI equals BI, that I is a free index. And it means this is actually 3 separate equations. A1 equals B1, A2 equals B2, and A3 equals B3. Free indices have to match on both sides of an equal sign. Now, on the other hand, if an index shows up twice, it's called a dummy index. That was the I in our dot product example, AIBI. It's just a placeholder for the summation. And because it's just a placeholder, you can rename it to whatever you want. So AIBI is exactly the same thing as AKBK. Getting this difference between free and dummy indices straight is absolutely crucial.
All right, now that we've got the basic grammar down, the summation rule, and the 2 types of indices, we need to bring in 2 special symbols. These are like the power tools in our toolkit that let us handle the really complex stuff, like cross products. So first up is this guy, the Kronecker Delta. It's written as delta sub ij. It has 2 indices, and its job is unbelievably simple. You can basically think of it as just asking a question. Hey, are these two indices the same?
And here's the answer it gives. The Kronecker delta is equal to 1 if and only if the indices I and j are the same. So delta 1, 1 is 1, delta 2, 2 is 1, you get it. But if the indices are different, like delta 1, 2 or delta 2, 3, it's just 0. It's basically a simple on-off switch.
So what do we do with it? Well, check out this expression, ai delta ij. The index I is a dummy index, right? It's repeated, so we have to sum over it. If we write that out, it's a1 delta 1j plus a2 delta 2j plus a3 delta 3j. Now think about it. Whatever value we pick for j, let's say we pick j equals 2. Only one of those delta terms is going to be non-zero. Only delta 2, 2 will be 1. All the others, delta 1, 2 and delta 3, 2, they're 0. So the only term that survives the sum is a2. So the whole thing just simplifies down to aj. This is called the sifting property. Multiplying by a delta and summing over one of its indices effectively just replaces that index with the delta's other index. This is one of our most important simplification tricks.
Okay, tool number 2 is the Levi-Civita symbol, sometimes called the permutation symbol. It's written as epsilon sub ijk. This one has 3 indices, and it is all about order and what we call handedness. It's the key to describing things that are anti-symmetric, which is a fancy way of saying they change sign when you swap 2 of their parts. And that makes it perfect for things like cross products. The rules for epsilon seem a little weird at first, but there's a simple logic. By definition, epsilon 1, 2, 3 is plus 1. Now, if you do an even permutation of those numbers, which basically means you just shift them cyclically, like to 2, 3, 1 or 3, 1, 2, it's still plus 1. But if you do an odd permutation, meaning you swap any 2 neighbors, like 1, 3, 2, it becomes minus 1. And finally, if any 2 indices are the same, like epsilon 1, 1, 2, the whole thing is just 0. This property is going to be really important.
Okay, we have our rules, we have our tools, we've got the summation convention, we know about free and dummy indices, and we have the Kronecker delta and the Levi-Civita symbol. Now it's time for the payoff. We're going to see how all these pieces fit together to create this incredibly powerful system for dealing with vectors. This is where you're going to have that aha moment. Just look at this table for a second. On the left, our old familiar vector notation. On the right, our sleek new index notation. We already saw the dot product, A dot B, becomes the super simple AIBI. But now, look at the cross product. If a vector C is equal to A cross B, then its ith component, Ci, is given by epsilon ijk ajbk. This is brilliant. It perfectly captures the whole cyclic nature of the cross product's components. You can see j and k are dummy indices getting summed over, and I is our free index, which gives us the 3 separate equations for the 3 components of C. And now we are ready. Let's go all the way back to that intimidating vector triple product from the very beginning. With all our new tools, we're going to prove the BAC-CAB identity. And you're about to see what would have been a full page of messy algebra turn into just a few logical, even elegant steps.
All right, step 1. Let's start with the left-hand side of that identity. And we're just going to find its ith component. We just have to apply the cross-product rule we just learned. The ith component of anything cross anything else is epsilon ijk times the jth component of the first vector, which is aj, times the kth component of the second vector, which in this case is the whole term b cross c k. It's that simple, just applying the definition. Okay, step 2. Now we've got to deal with that b cross c k piece. Well, that's just another cross product, so we just apply the rule again. The kth component of b cross c is epsilon kmn bmcn. Now notice I have to use new dummy indices here, m and n. That's because I, j, and k are already being used in this term. So I just substitute this new expression back into our equation from the first step, and now we have an expression that's got 2 of these epsilon symbols in it. And this brings us to the key that unlocks the whole thing. There is a very famous and incredibly useful identity that connects a product of 2 Levi-Civita symbols to a combination of Kronecker deltas. It says that epsilon ijk times epsilon kmn is equal to delta im delta jn minus delta in delta jm. That repeated index k is the one being summed over. This identity is the absolute linchpin for proving vector identities. We're not going to prove it right now, but we are going to use it to solve our problem. Step 3 is pretty straightforward. We take our expression from step 2, the one that had the epsilon ijk epsilon kmn product, and we just replace that whole product with the delta identity we just saw.
So now our whole expression is written in terms of deltas and the A, B, and C components. Yeah, it looks a little more complicated for a second, but it's about to get much, much simpler. And now for the big simplification. We're going to use that sifting property of the deltas. So let's distribute the AJ, BM, CN to both parts of the parentheses and take them one at a time. The first term is delta IM, delta JN, AJ, BM, CN. We have two sifting operations to do here. First, the delta IM acts on the sum over M. It sifts through the BM and replaces the M with an I, turning BM into BI. Then the delta JN acts on the sum over N. Wait, CN depends on N. It sifts through CN and replaces N with J, turning it into CJ. So that first term just becomes BI AJ CJ. Now for the second term, minus delta IN, delta JM, AJ BM CN. Same idea, the delta IN acts on CN, turning it into CI. And the delta JM acts on BM, turning it into BJ. So this second term becomes minus CI AJ BJ. If we put them together and just rearrange a bit to make it look nicer, we get BI AJ CJ minus CI AJ BJ. And that's exactly what's on the slide.
Now for the final step, we just translate this back into our old vector language. What is AJCJ? Well, that's just our notation for the dot product, A dot C. And what about AJBJ? That's the dot product A dot B. So our entire expression for the ith component is BI times the scalar A dot C minus CI times the scalar A dot B. This is precisely the ith component of the vector expression B A dot C minus C A dot B. And since we've just shown that the ith components of the left side and the right side are equal for any I, the vectors themselves have to be equal. And just like that, with a few clean lines of systematic algebra, the BAC cab rule is proven. No mess?
That was pretty powerful, right? But look, becoming truly fluent with this notation, it takes practice. And there are a few really common traps that students tend to fall into when they're starting out. So let's just go over them right now so you can avoid them and build your confidence up. Okay, here are the big 3 mistakes to watch out for. Number 1, mismatched free indices. An equation like AI equals BJ is just meaningless. It doesn't make any sense. The free index has to be the same letter on both sides of the equation, period. Number 2, reusing a dummy index in a single term. An expression like AI BI CI is totally illegal. You can't sum over the same index 3 times. An index can only be summed over once per term. If you need another sum, you have to use a new letter, like AIBI times CKDK. And number 3, getting confused about what an equation with a free index actually means. AI equals BI plus CI is not a sum over I. Remember, I is a free index there. This is really 3 separate equations: the x component equation, the y component equation, and the z component equation.
So how do you actually get good at this stuff? Honestly, it's the same way you get good at anything, you just gotta practice. The absolute best thing you can do is open up your physics or math methods textbook, go to the chapter on vector identities, and just pick one. Your first task is to translate it into index notation. Then try to use the rules, the delta and epsilon identities, to prove it. Doing this over and over is the single best way to make all these rules feel completely natural.
Okay, we have covered a ton of ground, so let's wrap this up with a final, super clear recap of the most important rules and ideas. Think of this as your index notation cheat sheet.
This table really boils it all down. You've got the summation convention. A repeated index means you sum over it. You've got the free index. It appears once per term, and it has to match on both sides of an equation. You've got the dummy index. Appears twice, gets summed over, and you can rename it anytime. Then you have your tools. The Kronecker Delta, delta ij, is your substitution tool, and the Levi-Civita symbol, epsilon ijk, is for handling anything with anti-symmetry and permutations. These 5 concepts, right here, that's the entire foundation.
So in the end, index notation isn't just some clever little math trick. It's a fundamental change in how we write down and think about physical laws. It's the language that makes advanced theories like electromagnetism, fluid dynamics, and especially general relativity manageable. Honestly, mastering this is an investment that's going to pay off for the rest of your time in science.
You now have this incredibly powerful set of tools. You can look at these really complex vector equations not as some algebraic nightmare to be survived, but as a puzzle that you can elegantly solve. So I'm going to leave you with this question. What are you going to go tackle first? Maybe the curl of a curl? Or dive into one of Maxwell's equations? The choice is yours. Thanks for watching.